All right, so we are covering some higher level content here, starting with a unit on complex numbers, beginning with complex algebra today. In this short kind of playlist of, I believe, 5 sections, we're going to cover all the things we need to know in higher level regarding complex numbers and hopefully look at some IB style problems as we go. So if you're keeping track on the syllabus, we are going to cover what is AHL 1.12, okay? That is dealing with this imaginary unit I, the definition that I squared is equal to -1. And we're going to look at the standard traditional Cartesian form of a complex number with that real and imaginary part. So Z equals A plus BI. We're going to talk about conjugates, we're going to talk about modulus, and we're going to talk about arguments in this section of videos. Okay? So let's begin with what we need to know about this imaginary unit. Okay, so the imaginary unit I is defined as the square root of -1. Okay, so you can think of this as a tool to solve a problem. Okay, that problem being, how do we take the square root of negative numbers? Okay, just using real numbers, that is impossible. So we've created this tool, this imaginary unit, to do that. Okay, so if we can take the square root of a negative number, it will involve a real number, but will have this imaginary unit I attached to it, and that's how we get to this idea of a complex number. Okay? So I is equal to the square root of -1, which means that I squared is equal to -1 itself, and these are two good things to know going into the IB exam. You might have learned them in an Algebra 2 class or in a prep class for your diploma program, but these are definitely things you want memorized going into that exam. Okay? So how do these help us? We'll dive straight in here doing some problems. These allow us to take the square root of negative numbers. Okay? So what we can do is take these two negative radicands and write them as -1 times a positive number. Okay? So the first one turns into the square root of -1 times 36, and the second one the square root of -1 times 49. We can then use properties of radicals to split this into the product of two radicals, and each of those has that I component in it coming from the square root of -1. Right? We can then simply combine these like terms. We can think of it like 6x plus 7x. Instead, it's just got this imaginary unit, so this will simplify to 13i right here. Okay? The second one, we look at the product of these two radicals. We just need to be a little bit careful here. Again, we are going to turn these into imaginary units first, and then simplify these down. Okay? So this will simplify to 6i times 7i, which would be 42i squared, and then using our definition of I squared, this is 42 times -1 for an answer of -42. Okay? If you need more practice working with that imaginary unit, there's plenty of that online, so you can definitely get caught up there. Okay? So numbers of this form, numbers that are just b times the imaginary unit I, okay? We refer to these as purely imaginary numbers. Okay? They are just a real number times this imaginary unit, and that is purely imaginary. Okay? A complex number is built out of a real number, which we call A, times plus a purely imaginary number, we call that BI. Okay? So we say here that A and B are real numbers, okay? And that gives us this Cartesian form of a complex number. Okay? This is the Cartesian form of that complex number. Okay? And we give them this notation, Z equals, you may see A plus BI, you may also see X plus YI as another form. Okay? A is what we call the real part. Okay? That's the part without the I attached to it. And then the B is referred to as the imaginary part. So this is just notation. This is just a language of complex numbers. This is how we communicate. And we have a symbol for that real part. So if we say RE, that stands for real part. The real part of Z is just A. So think of this real, this RE. This is a function that can just strip off the real part for you. There's a similar function for the imaginary part, that is IM. So the imaginary part of a complex number is just the number in front of that imaginary unit. Okay? It's not BI, it is just the B here. Okay? So it strips off that imaginary part and removes the I. Okay? We also have a symbol for the set of all complex numbers. That is the C with the line down, kind of like real numbers. So we're going to go through all the basic math operations in this class, starting with equality. Okay? So two complex numbers are equal if and only if the real parts are equal and the imaginary parts are equal. Okay? So this is what it means for two complex numbers to be equal. Real parts are equal and imaginary parts are equal. What this allows us to do when we're equating two complex numbers, we can make a separate equation with the real parts and a separate equation with the imaginary parts. Okay? So if we have A plus BI equals C plus DI, we can say A equals C, and we can also say B equals D here. Okay? That's equality of complex numbers. Okay? Addition and subtraction is very easy. Okay? We simply add the real parts together, and we add or subtract those imaginary parts. Okay? So the easiest way to think about this is essentially treating this I like a variable. It can combine like terms. It won't combine with non-like terms. You can multiply them together using exponent rules. You can just treat it as if it was your favorite variable, x, y, z, whatever you like. Okay? So we have 4 plus 2i minus 6 minus 4i. We can simply distribute the negative here to get 4 plus 2i minus 6 plus 4i, and then combine our like terms to give us 10 plus 6i as our final complex number from subtracting two complex numbers to start with. Multiplication is where it gets a little bit interesting. Okay? Again, we just treat those imaginary terms like our variables, and we always want to keep this fact in mind that I squared is equal to negative 1. Okay? So if I want to square a complex number, such as 2 plus 3i, I can simply do this as an algebra problem by multiplying it by itself. Okay? I multiply this out, and I will get 4 plus 6i plus 6i plus 9i squared. And remembering this fact I just had that I squared is equal to negative 1, okay? I can substitute that in for the I squared while combining the like terms. So 4 plus 12i plus 9 times negative 1. 9 times negative 1 is negative 9. I'll combine that with the 4. That would give me minus 5 plus 12i as my final answer for this complex number multiplication. Okay? That fits the form they asked me for in this question, given that they wanted it in the form A plus IB, where A and B were both integers. Here those integers are negative 5 and 12. One thing a lot of HL students don't know is that they can do a lot of complex number work on their calculator. Okay? So we'll jump over to our TI NSPI here to take a look at how that might go. Okay? So a lot of the things we need are going to be in the menu option, and we'll look at that menu and see what that can do for us. Okay? So we will add a calculator page here, okay? And we'll go menu, and we will look for numbers, algebra, calculus, nope, numbers, complex number tools, right here, number 9. Okay? So we can take the complex conjugate, we can take the real part, we can take the imaginary part, we can do some things with polar angles that we might not understand yet, but we've got all those functions built into our TI Nspire right there. Okay? We can actually begin with just playing around with the imaginary unit here, confirming some of the results we saw before. Okay? So we can do 2 plus 3, and then that I is going to be found in the punctuation menu right here next to your pi, and you'll notice it goes bold, and you can perform all the calculations we've already seen with this imaginary unit I right here. Okay? Now make sure you use the imaginary unit, not the I variable on your TI Nspire. That variable will just give you a regular I and not the imaginary unit I. Okay? So that's how you can do any kind of complex number calculation you like. Do 5 minus 6 I can do that to the power 4, right? And it'll crank all this stuff out for me. So super useful on paper too. Okay? If we want those more advanced operations, if I want the real part of that complex number, okay, I am menu, and then I'm numbers, and then complex algebra tools. I can do things like the real part, Okay, so I can ask for the real part of 5 minus 6i, and it'll just strip me off that 5 as the real part. Okay? So going back to our notes, we know that the calculator can help us as long as we're in menu, and then it's in number, and then it's those complex number tools. Okay? Complex number tools. Okay? All allowed, all unlocked on the IB exam. Okay? So we can run quickly through these calculations using our TI-Inspire. We'll do that. Okay? So the first one is 4 plus 5i minus 7 plus 8i. Again, we can do these by hand, but with our calculator, this is really quite easy and saves us any algebra errors. So we'll run through these real quick. We'll do that. Minus 7 plus 8. I'm actually going to copy this I so I don't have to keep selecting it. Just paste it. So this first one is negative 3 minus 3i. That's your complex number result. The next one is a product. So that is 4 plus 5i. And we just imply the multiplication on the TI-Inspire. We don't even have to type it. And you notice my first I is not bold because I used a regular I rather than the one I was copy and pasting. There is our result, 7 plus negative 7 plus 22i. Where it's really useful is going to be on division. We'll talk about how we actually divide complex numbers in a minute, but for now we'll just let the calculator handle this. It should give us a complex unit right there. 1 plus 2i, and it'll tell us that that is 8/5 minus 1/5 I. So super useful to know what the calculator can do for us, save us a lot of time on an exam. Okay? So what is actually happening when we try and divide two complex numbers? Okay? We're actually multiplying the numerator and the denominator by what's called the complex conjugate of the denominator here. Okay? And I guess we should define what a complex conjugate is. We'll do that first down here in the blue box. The complex conjugate of z equals a plus ib. We denote that with this z star. We put this little star where the exponent would be, and the conjugate is simply the same thing, but we've changed the sign on the imaginary part. So a minus bi. Okay? And you may see a couple of different notations for this. I will typically use the star as the notation I like. So I like z star. You will see some people use maybe more of like a function, conj. That's another way of saying conjugate. You may see some people use a prime to denote their conjugate as well. But I usually go with the star, as does the IB. Okay? So how does this help me divide two complex numbers? It allows me to take my complex numbers that are being divided and multiply top and bottom by the complex conjugate. So the conjugate of 1 plus 2i is 1 minus 2i. And I perform this operation now with multiplication. The top will simplify to 2 plus 3i minus 4i minus 6i squared. And what will happen with the denominator, we've created a difference of 2 squares, so we will get no middle term. So this will simply be 1 minus 4i squared. Combining our like terms and remembering that I squared is negative 1, we will have 2 minus 7i, minus 1i. Okay, this will turn into plus 6 when we do our I squared equals negative 1, and we will have 1 plus 4 in the denominator. Okay? Pretty easy to see from here. This will combine to 8 over 5 minus 1 over 5i, which is the same result the calculator gave us. Second problem gives us another complex number division, but in this case, the division is purely imaginary, so we are just dividing by 8i. Okay, you can multiply by the conjugate here, which would be negative 8i, but it is much easier to just multiply by the imaginary unit itself to make that denominator real. Okay, so we can simply multiply top and bottom by I here to get the same result. Okay, so this will give us I minus I squared on top and 8i squared underneath. We know I squared has a value of negative 1, so this will be negative 1 plus I on top, and this will be negative 8 in the denominator. again, simplifying to split to a real and an imaginary part, 1/8 minus 1/8 I is our result there. So this is the use of the complex conjugate. We've already defined it. Okay? We want to go ahead here and give the most important property of that complex conjugate, and that is that any number times its conjugate is always real. Okay, so this is what the conjugate is really used for when we're rationalizing or we're dividing those complex numbers. We're trying to make the denominator real. Okay? And we'll go ahead and prove this little result that it's always real. So we'll say z equals a plus bi, which obviously means z star is a minus bi. And we'll take the product of these, so z times z star. This is a plus bi times a minus bi, which is a difference of two squares leading to a squared. I'll do the full multiplication. This would be abi plus abi minus b squared I squared. We can clearly see here the two middle terms will cancel out, and our result will be a squared plus b squared, which is obviously real, as a and b are real numbers in our complex number. Other properties of complex numbers and complex conjugates that you should know, and I'll do a few proofs of these. If you conjugate a conjugate, okay, so if you take the conjugate twice, okay, you will retain the original complex number. So z star starred will turn back to z. Property number 2 is a number and its conjugate are equal if and only if z is real. Okay, so the only way a complex number can equal its conjugate is if there is no imaginary part. If the bit you are changing on the sign on is 0. The third property is the conjugate of a sum. It is possible to prove that this is equal to the sum of the two conjugates. Okay? I might go ahead and prove that one down the bottom. The fourth one is the conjugate of a negative of a complex number. This is simply the conjugate of z negated. So you can interchange the operations of conjugation and negation right there. The fifth one is the conjugate of a product that is equal to the product of the two conjugates. We can prove that one as well. And finally, the conjugate of a complex number raised to the -1. This is the conjugate raised to the -1. Again, you can interchange those operations. Okay? So these seem quite abstract. We'll do maybe 2 proofs of these. I think I'll prove number 3 and number 4. Okay? So the proof of 3 is very simple. You say z1 equals a plus bi. You say z2 equals, I don't know, c plus di. And then we go ahead and add these two complex numbers, or maybe compute their conjugates. Let's compute their conjugates. Let's do it that way. So the two individual conjugates would just be changing the sign on the imaginary component. And then if we add these two conjugates together, z1 star plus z2 star, this will be a minus bi plus c minus di. If we collect the real parts, that's a plus c. We collect the imaginary parts, this is minus b plus di. And it's pretty straightforward to see. This is a plus c minus b plus di. That's the same, but what is this a plus c? This is simply z1 plus z2 conjugated, because a plus bi is z1 and c plus di is z2. Okay? So that's how you complete that first proof, and you can do a similar thing for any of the others there. Okay? I'm actually going to stop at 1 just to keep this video short. So hopefully you've got a feel for complex numbers and how those work. In the future videos, we'll look at more interesting things such as complex polynomials, as well as taking powers and roots of complex numbers. So thank you guys for watching, and stay tuned for more content.